Good morning, everyone, and thanks for coming this early in the morning. I'm Desi from University of Virginia. So yesterday, you have already seen some papers on metadata normalization that tries to minimize the effort, the manual effort required within a building. But today, I'll talk about our work as a first step towards normalization with no manual effort. So before getting to that, let me remind you why we are doing this metadata normalization. So we have been working with a company. They have a building management system. The company is called Tree. So who has developed several powerful analytic engines. They want to sell these engines to the customer based on the energy savings they can generate. So as you saw from yesterday, it's hard to map the points in building to the input of an analytic engine. So technicians have to look at these cryptic point names, and they usually have, these people usually have domain knowledge. So even though often they have to actually visit the building to to visually inspect the point in order to get this mapping done. So you see, oops. Yeah, they have to do this manually. And this process can take this process can take a week or even more and makes it hard to sell their products. So techniques introduced from yesterday, they can actually significantly reduce this manual process, but they don't eliminate it. So a company like Tree, they must still investment in customer before it can demonstrate value. This is not an easy way to achieve their sales. So a customer wants to see the expected energy savings before buying their analytic engines. But Tree cannot show the values before they finish this mapping process, which can take a week or more. So we envision a world where a company like Tree, they can easily apply their analytic engines to any building instantaneously, so that customers can easily see if they want to buy it or not. So in fact, many analytic engines can be effortlessly applied to thousands of buildings across the globe. And people can choose the engine that works best for them, and they can buy that one. So this will create a market for these kind of analytic engines. Well, however, to achieve this goal, we need to completely eliminate this human from this mapping process. Even though the resulting process might only able to produce an approximate mapping, but it will be still helpful in producing a market for these analytic engines. So our key insight behind our solution is that a company like Tree, they usually have many already fully labeled buildings. So given a new different building, although no two buildings are identical, but most buildings are similar to another in one way or another. So for example, one pair of building, they may have a similar mechanical ventilation system, while the other, they may have similar lighting condition and lighting systems. So these similarities result in similar values in the data streams themselves. And our hypothesis is that we can automatically infer the metadata structure of one building given the known metadata structure from another building. So another thing is if we have more labeled building, then that inference will just get better. So next, I will walk you through the detail of the approach. So our insight actually of the approach is that usually we have labeled buildings. So here you see some. Oops. Anyway, so here you see some points that are labeled from one building. And then, given a new building, we can use the information from this already labeled building to help the prediction on the new building. And one source of information from the labeled building is the point names. So they are a good indicator of the type information, but they are less likely to be consistent across building. So for example, here you see they have clear pattern within a building, but they are less consistent across building. So if you want to use something learned from one building, apply to another, that doesn't quite work. But on the other side, another source of information is the data we have associated with each point. So this point usually have a similarity for the same type. For example, room temperature, they will always be between 60 to 70 degrees, no matter which building it is in. So our insight is to combine this complementary strength of both attributes and do this task. So we adopt the setting of transfer learning from machine learning. So we first learn some characteristics from the data in this labeled building, and then we transfer that to the second building to help do the labeling. For example, using this information from the data, we can label the points in this labeled new building. But this labeling is not perfect. So how do we tell if these are correct or not? Then we have this source of we have another source of information, which is the point name. Because we believe point names within a building have more patterns or regularity. So we want to use the information from the point name also and compare them against the labels produced by the data. For example, in this case, you see 2 point names of 2 different points, but actually the label generated by the data are different compared to the point names. So then we know that this is very likely to be a mistake. So from there we know, okay, maybe we have the able to throw these wrong labels. So let me give you the detailed steps of the approach. So actually there are 3 steps. The first step, we start from this label source building, and then we can learn a classifier using the data because we believe data is more generalizable across buildings. But usually, if you use only one classifier, that might not work well on all the example in the target building. So we train a bunch of different classifiers. It can be a decision tree or linear regression or whatever. So after we got this a bunch of different classifiers, so suppose we want to predict the one in the middle in the target building. So how do we effectively combine all of these different classifiers? So the key is usually if we have the ground truth label in the new building, then we can easily measure the confidence of the prediction of each classifier. But that's not the case in practice. We don't have any true label for the new building. So how do we approximate that? So we have the assumption that the cluster structure on the point names in the new building can somehow approximate the true structure. So this is again based on the insight that the point names in the same building usually have strong pattern. So we run this clustering on the new building where we got, you see these color circles, each one gives you a cluster. The next step is to use this clustering structure that helps you to measure the confidence of each classifier. So for example, here we can apply the first classifier to the same points and then the labeled points with the color shown on the slide. So then we can do the same thing for all the classifier. Again, we use the second classifier and do the labeling. So what we want to do here is we can compare the structure from clustering and classifier on the same population, and then we see if they are similar enough or not. So here you see clearly on the top, the structure given by classifier is more similar to the one given by cluster, which we believe is the true structure. So following this out, then we just know, okay, we can assign a larger weight to the first classifier because it is likely to do a better job in prediction. So this is the high-level idea of the approach. And there are several key design points missed here. So the first one is how do we generate the data features? Because this is the key part for building classifier and applying them across building. So given a data stream, we just do something similar to what you have seen from yesterday. We do the windowing on the trees, and then within each window, we compute several different statistics. For example, for the mean function, you can get this n tuple over the entire trees, and then you can further collapse that into a smaller feature vector by computing some statistics. So this is the way we construct the data features. And the next question is how do we turn these raw point names into a feature vector, which we can use for clustering. So given that primitive sensor point name, then we just take out all the numerical digits, keep the alphabets. And next, we use some common feature used in protein analysis, which is called KMERs. So what KMERs basically does is, given a string, it computes the substring of length k. For example, given that A, B, C, D, E, F, G, if k is set to 3, then you just compute all the substring of length 3 within that given string. So this is how KMERs work. So suppose we set k to 3, and then we can compute all the streamers of that set of points. And then every time we got a new point, we just do the similar thing, compute all the KMERs, and then count the frequency of each term within that big set, and then we can turn this into a feature vector. And here, one means, okay, that the 0 and string happens once, and if there's less than 0, then that means there's no such a term. So, well, I also want to throw in the mathematical definition of the weighting function, if you remember. So this is the same structure you have seen from last slide. So here we have two different classifiers, and I also show the structure on the same population given by clustering and classifier. So the way we weight each classifier is to compute the similarity between these two different structures. So basically, we want to count how many common examples given by the two different perspective, and over all the total different number of unique examples. For example, on the left, you see, okay, the cluster and classifier, they have labeled 5 different examples, and they have 5 out of 5 in common. And on the right, they have only 2 in common out of the 5 total unique examples. So that's the way we compute similarity. And once we got the similarity, we can easily do this normalization and get this weight for each classifier. Another thing we noticed was that, so in some cases, this similarity can be quite low. That means we cannot trust the structure given by this classifier. So we just need to look at the average similarity across all the classifiers and then set a weight on that, set a threshold on that. That means if the average similarity is not high enough, then the quality of the prediction is not usable. So this is the important parameter delta, which is the threshold we use to evaluate our approach. So this is the detail of our approach, and then we use a data set containing 3 buildings from 2 different campuses, as you see from here. The left one on the bottom is our CS building, the other 2 is from Berkeley. And we use over more than 2,000 points of 22 different types, and we also use 7 days worth of data to do this evaluation. Well, we want to see how it works, so we set up some experiment. Well, because this is transfer learning, we learn the information from one source building and transfer to another. So we do this pairwise for each 2 buildings, and then we repeat the same experiment for all 3 pairs buildings. Well, now we also repeat it with different thresholds, which is the parameter you saw from last slide. And particularly, we construct several different classifiers during that first step. In this case, we use random forest, linear logistic regression, and SVM. So we also use 2 metrics to evaluate the approach. So one thing is the coverage, which is how many percent of the points in the new building we can label. The other thing is the accuracy, which means out of that percent got labeled, what is the accuracy? So this is the setting, and I'm just showing you the result from one pair of building between building A and building B. So here you see on the x-axis is the threshold we set on the weighting parameter, and the y-axis is the percent. So here you see on the left, when we set a very small threshold, that means we just generously using all the prediction for the new building. There you see, okay, we got a very high coverage. But at the same time, the labeling accuracy is quite low, so it's right up below 80%. But as we increase the threshold on the weighting, then we see that though we got less example label, but in return we have better quality of labels. So this tells you that, okay, we we have an important parameter to set, which is the threshold. And we empirically set this threshold at 0.4 to get a good balance between this coverage and accuracy. So here there are 4 curves, and each side contains 2 curves, and they show you the accuracy and the coverage. Another important question we ask is, can we combine this approach with some other approach can be used within a building? So, well, we have 2 different settings. So the first setting is we first run this fully automated approach on a building, and then we got a good starting point. And after that, we can use some active learning-based approach like the one you see from yesterday. And the second approach is just running that active learning approach alone, which requires human labeling. So here you see the result on the right, that the blue curve is our combination approach. So we start by using our approach, and then we switch to a active learning-based approach. So the 2 curves are close to each other. There's no big difference. It looks like the only improvement is a good starting point at the beginning. So well, that's the result from here, but we also but we also look at another different side experiment. So in the previous curve, you see that we're only doing this transfer between one source building to another target building. So what if we just throw in more source buildings? So here we experiment with more source buildings. In this case, we have 2 source buildings to transfer to one target building. So here you see on the left, this set of bars tells you that on average, if we add in 1 more source building, we can get about 2 to 3% increase in the accuracy. And also at the same time, we got about 2 to 9% increase in the coverage. So this experiment is encouraging because it shows that if we throw more source buildings, we can get both better accuracy and coverage. And this kind of in return helps us to get a better starting point at this point. So we believe if we get more sources, then we get more promising results. So there are some important points to make. So first one is we want to try more buildings as the source to do this transfer learning. And also the other thing is we didn't use any customized data features. We just used some common statistical features. But we believe this is an important key to us. So for example, some important domain knowledge, like once you see something happen in the occupant sensor, then you will see some correlation in some other readings like the light. For example, people walking in the room and the light turns on. So this kind of correlation as domain knowledge will help do this feature extraction. The next point is about weighting function. We just use some simple locally weighted function which limits the usage of the approach. And one last point I want to investigate more is what kind of accuracy is required for a certain application. We didn't do any study on that, but we believe that's an important direction. So before I conclude, there are also some related papers from this year or previous year. And they all, like I mentioned earlier, so they all try to minimize the effort within a building, but do not eliminate it. So our work is different in the way that we try to eliminate this manual effort completely and doing the mapping automatically. So to conclude that, we used the complementary attribute of the points, the complementary attribute of the point, which is the data and the point names, and we also developed a technique to do this mapping automatically. And we see that we have some promising result, and we believe this is the right direction to explore. Because once we got this manual effort eliminated from this mapping process, it can be more scalable. So one last thing to note is we are more than happy to share our data set and the code, so that can hopefully accelerate the study on this method and normalization. And I will wrap up here and take any questions if you have. Thanks.